Now there are two terms. This is just actually background on doing. We have two terms. One is called strong scaling, another is called weak scaling. See, remember we are discussing about multiprocessing, multithreading, and parallel vectorization. Where these are, in effect, all of them are parallel computing. So whenever you are doing parallel computing, you have to think how much performance is improved. So strong scaling shows how the solution time varies with the number of cores for a fixed total problem size. That means, suppose you are solving one problem which has 1 million tasks. So instead of 2 machines, if you go to 4 machines, then how much solution time has reduced? That is called strong scaling. So that means if you use double the number of machines, you can solve it in half the time. Okay. Now, weak scaling is how the solution time varies with number of cores for a fixed problem size per core. Okay. So if the size of problem which is you allocated to each core remains fixed, then how much performance is improved? So, for example, if your data set is doubled, that means your overall problem size is doubled, then you can use twice the number of machines so that your problem size per core remains fixed and your solution time also remains same. Okay, so sometimes you know what happens when you are increasing the number of machines, your problem size does not increase, but sometimes it can also increase. So that's why these two are different definitions. I mean, different ways of calculating the speed depending on the different scenario. Okay, now we will. Any questions? Yes, any questions?
Yes, so please explain weak scaling again.
Okay, weak scaling means, so let me take an example. Suppose you have 1 million search queries. Okay, and when you have only one core, it takes, suppose 10,000. It takes 1,000 seconds. Okay, it takes 1,000 seconds. Now, suppose you add. Now you add 2 instead of 1. Now you suppose you have 2 cores. Okay. So if you are using this idea of strong scaling, okay, if you are using the idea of strong scaling, then with 2 cores, your solution time should ideally reduce to 500 seconds. And then your strong scaling speed up is 2x. Okay, which is the ideal speed up, because if you increase the number of cores by 2, you have achieved a speed of 2. That is really ideal. That's really linear speed up. That's the best you can get. Okay. Now suppose another case. You had this as the original. So suppose originally you are working on CFAR10 dataset, which has 1 million whatever queries or images. Now you move on to ImageNet dataset, right? Which has 16 million images or queries, whatever. Right? It has 16 million images. So now instead of 1 core, suppose you also move to 16 cores. Suppose you move to 16 cores. Then previously you were taking 1,000 seconds. Okay. Now you may still take 1,000 seconds. Suppose if you still take 1,000 seconds, right? Then your weak scaling is ideal. Okay, your weak scaling is you are getting 16x speed up with weak scaling. But suppose if your situation is not ideal, instead of 1,000, the execution time becomes 2,000, right? Which may be more realistic scenario. Here, what I'm writing constant time, that is the ideal scenario. It may not always happen. So suppose your suppose your execution time increases to 2000 seconds, then on increasing the number of cores from 1 to 16, your speed up you have got is 8x. Okay, is that fine? So
Yes,
both these cases are measuring the speed up. It's just that the scenario is different or assumptions are different. Here we make sure that the total problem size remains fixed, so 1 million queries. And here, sometimes as you, for example, in cloud scenarios, when they scale the capacity, they do it only when the problem size is scaling, right? You're moving from one neural network to bigger neural network or bigger neural network. That's the scenario in which these two different scalings are measured. Okay, now we'll discuss two paradigms. So one is shared memory, another is message passing. And this extra. So here you remember, right? We did this. Here we use message passing, and between the threads we will use shared memory. Let us discuss what they are. So in the shared memory, all the threads share the same virtual address space. Okay. So for example, all the threads which are running on my desktop, they all have the same RAM. They're sharing the same address space. They can communicate with each other by reading and writing values to the shared memory. Okay, because there is a memory which is shared, so they don't have to explicitly send messages to each other. Each thread does not need to. Whenever they need to communicate, whenever they need to synchronize, they can synchronize using this shared memory. And application has to ensure there is no data corruption. So you remember the example of bank, right? Someone withdraws from the bank, someone deposits in the bank. Unless you put the lock, it will always lead to some mistake. So that means lock means only one person can enter. Only one person can either read or write. Right? So only when that access is finished, only then next access will be allowed. And that is achieved using lock and unlock or atomic. There are different mechanisms for that. So an example languages of shared memory paradigm are OpenMP, CUDA. So in this course, I'm not discussing any of them because I want to quickly start discussing the hardware accelerators. Now, in the message passing, here programs communicate between each other by sending and receiving messages. Here, they do not share the memory. Their memories are completely separate. So that's why message passing can scale to very large number of processors. For example, if you see like supercomputers, so a supercomputer may have 10,000 nodes. Now, for example, when I was at Vocational Lab, so still I think now that I think Summit supercomputer is #2 in the world. So a whole very big room. It had different racks. Each rack has many servers inside it. Okay, so whenever they need to talk to each other, they will send messages. And if you start sharing the memory, where do you keep that memory? It's not that even physically they are not close to each other. Physically, they will be separated from each other by 5 meters, 10 meters. So shared memory does not scale very well. Okay, whereas message passing here, only when they need to talk to each other, they will send messages. So here they do not share the memory address spaces. And the languages which implement message passing paradigm is MPI. So MPI is a standard. Now different vendors can have their own implementations. For example, Intel has its own Intel MPI and so on. And there are open MPI also. So open MPI is within this category. Open just shows that it is open source. Okay. So message passing is a different paradigm than shared memory paradigm. Okay, now we will discuss Klein's taxonomy. So this is very popular. You may encounter it many times. So here there are two things. One is the instruction stream. That means what are the instructions we are executing, and what are the data items that we are executing. That means what are the data values on which we are operating. For example, if you have A plus B. So here plus shows the instruction. That means do the add operation. And on what? That means do the add operation on A and B. These are the data streams. So based on the 4 possible combinations, you can have 4 types of multiprocessors: SISD, SIMD, MISD, MIMD. Okay, so in SISD is the standard Uni Processor. You have just one. It's like scalar operation. Okay, so you have one instruction and you have maybe 1 or 2 operand or 3 operands on which it works. Now SIMD is very interesting. Okay, here one instruction, that means single instruction, operates on multiple pieces of data. Okay, examples are vector processors that have one instruction that operates on many pieces of data in parallel. For example, one instruction can compute the sine inverse of 4 values in parallel, or we can have 4 additions. So suppose A plus B, C plus D, E plus F, G plus H. So here we are giving 4 separate instructions. But if we do SIMD, we'll just give one instruction: A, C, E, G, and then we have B, D, F, and H. So same addition operation, but operands are 4. So in single instruction, that means we need to now execute less in number of instructions, but each instruction is more powerful.
Sir, MATLAB uses SIMD processor.
No, MATLAB is working on matrices. So there the operands are matrices. So you are adding one matrix with another matrix.
Sir, but there similar thing happens.
So
addition and so.
Because here it is how the hardware will execute. So if for example MATLAB is accelerated over GPU, which is example of a vector processor, right? Then you can see. But see, MATLAB is just a software. Right? MATLAB is a programming language. Now, when you are if MATLAB is operating, suppose on your mobile phone, some old mobile phone, right? Then how are those? Suppose you have like 3x3 matrices which you are adding. Okay, you have one 3x3 matrices, another 3x3 matrices. So MATLAB will say that okay, add, do element-wise addition. So to you, it appears as if it happens in a single instruction, but in the hardware, whether it takes a single instruction or whether it takes multiple instructions, that depends on the hardware. So if you remember tensor core can directly multiply 2 matrices with a single instruction. Right? That if you have that hardware, then fine, that's called SIMD. But if you don't have that kind of hardware, if you just have just simple adders and multipliers, one adder takes 2 inputs, 2 scalar values. That's not SIMD. Here we're talking about the hardware.
Okay.
So what you're saying, I mean, in terms of software, of course, you can say, okay, we are multiplying 2 matrices, but that is just your software level, your abstraction. How it's getting implemented in the hardware, that's what we are seeing. Now, MISD is multiple instruction single data, which is somewhat rare in the practice. So this is just one example. Consider an aircraft that has 3 different processors. These are the names of different ISA. We have MIPS ISA, ARM ISA, x86 ISA. So they operate on the same data. See, because whenever you are flying an aircraft, you need to be doubly sure that you are doing the correct execution. Right? So you do the execution 3 times and you compare the results. If the results are same, then your answer is correct. If even one of the answers are wrong, then you do something. For example, you might have gone to some bank, and the cashier, he will first count the money with his own hands. Then he will have money counted with the automated counting machine, and that took 2 times. So if all the 3 times the answer is same, then he is really satisfied. If even one of the times answer is wrong, then his heartbeats are increasing. So he will really then very, very slowly do the counting. So the idea is because that's very, very crucial. The point is it's very, very sensitive. Any money he loses, he has to pay from his own pocket. Similarly, aircraft, you can't afford to commit mistakes. So that's why you check it 3 times. So here there are we have 3 instructions operating on the same data. The final outcome is decided on the basis of a majority vote. So majority vote means if you suppose 2 are matching, and third is not matching. So you always assume that at most one will be wrong. If more than one is wrong, then forget. Then, which is rare event, because mistakes are rare. These mistakes are supposed to be rare. Suppose MIPS and ARM match with each other. Suppose x86 differs. Then you conclude that x86 is wrong. You don't conclude that MIPS is also wrong, ARM is also wrong. Right? Because in general, not everybody will not fail at the same time. That is MISD. Now, MIMD is multiple instruction, multiple data. That means here, this whatever your processing units are there, they're working independently. They are fetching different instructions, and they are operating on different data. And now within this, you can have two further types. One is SPMD, where you have a single program, multiple data. So for example, OpenMP or MPA programs, we typically have multiple processor threads executing the same program with different inputs. So the program is same, but each program has multiple instructions. Okay, that is SPMD. And in MPMD, we have multiple program, multiple data. So here programs are different, data are different, and each program is running multiple instructions. So it is really very different. Everything is different. So here what happens, master has master and slave model. Master runs a different program, slave runs different programs, and they do different computations. Okay, this is the Klein's tax. So the whole point of Klein's taxonomy is to define these 4 types of multiprocessors. One of them is actually Uni Processor, but it's called multiprocessor. Okay, here is a summary. So in SISD, single instruction operates on single data element. In SIMD, single instruction operates on multiple data elements. Actually, we have not discussed this array processor, vector processor in detail, so you can ignore the examples. Now, in MISD, multiple instructions operate on the single data element. Now, we will next discuss systolic array. Probably next month, we'll discuss systolic array design. Again, streaming processor we will not discuss. And one more example of MISD I gave is that when you verify the computation using different processors. Now, MIMD has multiple instructions operate on multiple data elements. So then you have multiple instruction streams. So examples of these are multiprocessor and multi-threaded processor. Okay, so now we'll first discuss multi-threading. So till now we were just discussing the background. Now we'll come to multi-threading. So here we have the idea of threads. Okay, so what is a thread? A thread is one execution context. So we spawn multiple threads. What is the property of thread? What is a thread? A thread has its address space shared with other threads. That means within different threads we have shared memory order, and every thread has its own program counter. That means every thread is executing on an instruction stream. Okay, for example, in a layman's language, suppose you have on your computer a Word, PowerPoint or Excel applications running. So it may be that each thread is running one application. Word is run by one thread, Excel is run by another thread, browser is run by another thread. So each thread is doing its own separate execution. Of course, they're sharing the memory. So each thread has its own program counter, register, stack. A process contains multiple threads, and thread communicate by the shared memory. That they have the shared memory, so through that they communicate. So this is how a usual program may work. A parent thread may be there. So initially we have only one thread, and at particular point of time we spawn. That means we start multiple threads. Right? If you remember, then the GPU, we said that initially only CPU works, then GPU comes. So here it's, of course, here it is all about same processor, CPU only. But if you are not using GPU, suppose we are not using the GPU, then what happens? We can, whenever intensive computation comes, we can run it on CPU itself using multiple threads. And finally, when suppose you are running the for loop, when the for loop is finished, then you just do thread join operation. That means you kill the this extra threads, and after that you again have sequential section. So in multi-threading, we have multiple threads on the same pipeline. Okay, we can run multiple threads on the same pipeline. So there are three types of multi-threading which are possible. One is coarse grained, fine grained, and third is simultaneous. So let us see their definitions. So before I explain them, let us see the simple analogy that will make things very clear. Suppose we have a car which is shared by 4 people, A, B, C, D. Okay. Now one option is that every time 4 people ride the car simultaneously, almost all the time. Whenever they want to go to their destinations, they run it simultaneously. Option 2, that for some point of time, for some days A uses the car exclusively, that time B does not use it. Then B uses it exclusively, A, C, D, they don't use it. Then C uses it for some days. It could be exactly same or almost same, that doesn't matter. Then D uses it for some days and then repeat the same pattern. Here also you can say it is sharing is happening, right? Car is getting shared. Here also sharing is happening. Here idea is different. In option 3, A uses car for some amount of hours, B uses it for some amount of hours, and C uses it for some number of hours, then D uses and then repeat. Okay, now you match these 3 options to these 3 types of multi-threading. Anybody can guess?
Sir, option 1 will be simultaneous, sir.
Okay.
And the option with the days, second one will be coarse, and third of they've been using hours. Option 3 should be fine.
Yes, fine grained. Yeah. So this is simultaneous means the threads are simultaneously running. And coarse grained means they are sharing, but at a coarse granularity. They are not simultaneous, but they are sharing one after another at the coarse granularity. And fine grained is they are sharing one after another, but at a fine granularity. So now let us see coarse grained multi-threading. So assume that we want to run 4 threads in a pipeline. So we run 1 thread for n cycles, run thread number 2 for n or almost same cycles, and so on. So they are using the same pipeline, but not simultaneously. 1 thread runs, then second, then third, then fourth. So assume that thread 1 has an L2 miss. So at least I hope what you at least roughly understand what is an L2 cache. Okay, L2 miss. So here, whenever you have a miss in any cache, you have to go to the main memory. So it takes 200 cycles. Okay. So while the thread 1 is waiting, you can schedule thread 2, right? You don't have to really wait till this 200 cycles. Meanwhile, you start something else. Now, if thread 2 also has an L2 miss, don't need to wait. Start next thread. So in this way, we can have a sophisticated algorithm that switches every n cycles, or when there is a long latency event such as an L2 miss. So here we try to minimize the idle cycles for the entire system, right? Because while one is waiting, we can start another. Here, so that was coarse grained, right? So here you can see coarse grained, this n value is usually large. Okay, and here even this weight granularity is large, 200 cycles. In fine grained multi-threading, switching granularity is very, very small. Here value of n, that is very small. So advantage is that we can take advantage of low latency events such as division and or L2 cache misses. So division is, takes suppose 5 cycles or 10 cycles. And L1 cache miss means whenever L1 cache misses, you go to the L2 cache. So here you are really very, very rapidly switching from one thread to another. Okay. So here we minimize idle cycles to even a greater extent. And of course, there will be correctness issues so that you can ignore. So Okay, now this is simultaneous. So till this point we discussed fine grained. Now let us discuss simultaneous. So most modern processors have multiple issue slots. That's why here we can simultaneously run
Sir,
three threads. Yes, please.
sir, in last slide, how we can minimize to a greater extent?
See, in coarse grain, right? Suppose in coarse grain, suppose if we have an L1 cache miss or if we have a division, then we don't switch. We have to wait for them. Only when a long latency event comes, then only we will switch. Right?
Okay.
Here, you know, as you can understand, like here is maybe you imagine some person who wants to save every minute of his time. Right? Whenever something he has to wait, he starts something else, starts doing it. Whenever something else waits, he starts doing something else. Whereas here you can see coarse grain means okay, if only something will come after 7 days, then I do something else. So that is the difference.
Okay.
Okay. In simultaneous multithreading, actually, here the idea is we can have more hardware, right? We can have 3 issue processors. That means we can simultaneously issue 3 instructions per cycle. So here we can do fetch, decode, execute for all these 3 threads. That means for one instruction can do fetch, decode, execute. Another instruction can do fetch, decode, execute. Third instruction can do fetch, decode, execute. So 3 threads can run simultaneously. So if a benchmark has low instruction level parallelism, then fine and coarse grained multithreading cannot help. Actually, if you can ignore it right now. I mean, we have not discussed too much of architecture background. I just want to quickly introduce simultaneous multithreading. So this also I will remove. Here, this figure is important. I will remove some of the slides because I don't want to go too much into basics of architecture. So here, coarse grained, you can understand. This is just for illustration, not to scale. Only after a long time. So here we have issue slots. We have 1, 2, 3, 4. We have 4 issue slots. That means each slot can issue 1 thread. Right? Each slot can issue 1 thread. So we have 4 issue slots, but only one of the thread is running initially. Then we switch to another thread. Then we switch to another thread. Then we switch to another thread. And that too after coarse granularity event. That means large latency. Here we can switch after probably every 5 cycles or 2 cycles or 3 cycles. That means it is much more frequent switching. And here, at any point of time itself, we can have more than 1 thread. So here we have more than 1 thread. Here we have more than 1 threads. Here only 1 thread, but here more than 1 thread. Here more than 1 thread. That means simultaneously we can have more threads running. And as you can see here, we can finish our task faster. So 4 and 5. So that is done. So here you can see our task is done faster. Time here it takes only 5 cycles. Here it takes 3, 5, 8. Here it takes 8 cycles. So at least for this example, simultaneous multithreading is much better. Any questions till this point? Now let us see vectorization. Now vectorization is slightly more involved. So remember this big picture. Now we have discussed MPI. We did not go into too much detail. I mean, we did not discuss too many types of it, but we just introduced how message passing involves sending messages. Because I don't want to go into programming language. Actually, programming language is a separate course in itself. I have already taught that course once. So OpenMP here we use, this is for this threads use shared memory paradigm. Now we'll come to the vectorization. So here is the summary of vectorization. We could have either scalar instruction, whereas compared to it we can do vector instruction. Just one vector instruction can replace multiple scalar instructions. And here the definition of vector length is very important. Here the vector length is 4. Now these are some of the SIMD instruction sets used, especially I think in Intel. I don't know whether others may be also using it. And you don't have to memorize it. So previously the register size 80 bits. Register size of 80 bits. For that we had instruction set MMX. Nowadays Intel processors, they can have AVX 512. That means it can operate on 512-bit register. Now suppose each operand is 32 bits. Then what is the vector length? If each operand is 32 bit with AVX 512, what is the vector length? Mohit? Yeah, sorry?
16?
Yeah, 16, yeah. Because you have to 512 divided by 32. Right? So that is 16. That means here, see, here you could add only 4 elements. Whereas with this kind of scenario, you can add 16 elements. 16 single precision numbers you can add in a single cycle. Okay.
Sir, can you repeat it once again?
See here, you have a very I'll show this with an example. Yeah, here. So here, suppose we have. So see here we are showing only 1, 2, 3, 6 byte. But in the example I'm showing here, it is 16 byte. So suppose take an example of 6. So here we have very wide registers. Okay, very wide registers. So here and so this 6 now 6 and each operand is 32 bits multiplied by 6. Okay, that is 192, right? Okay, 192. So if you have 192 byte register, similarly here it is 512 byte, 512 bit register, but in this example it is 192 bit registers. Then you can store different scalar values. One will be stored here, 132 bit value will be stored here, one will be stored here, one will be stored here, one will be stored here. And when you add them with a single instruction, you will add, and the addition of this and this, that will be stored here. Addition of this and this, that will be stored here. Addition of this and this, that will be stored here. But you need to issue only one instruction. That one instruction will operate on 6 different operands. Is it clear?
So that 32-bit is for data, right? Not the instruction.
32 bit is for the data. Yeah, your operand size is 32.
Data,
just like
okay.
it could be integer or float.
So that is not operand. Operand is plus minus. Okay, operator.
That is the operator. Operand is the data, right? Your operand can be either single precision. So if it is single precision, it is 32 bits. If it is double precision, 64 bits. If it is half precision, 16 bits. So depending on with this vector, vector length. This is not vector length we are defined as this, but vector length here is 16. But this is the operand width. And if you see in tensor in the Turing tensor core, what is the smallest data type that was supported in Turing's tensor core? Anybody remembers? I told you to remember that point. What is the smallest data type that is supported in Turing tensor core in the Turing GPUs? Anybody can guess or recall?
Local where?
Sorry?
Local where?
No. You could not understand the question. So, okay, I think, so it was int 4. Okay, that was the smallest, that means just 4-bit wide integer. So now you can see if you had such a wide, SIMD registers, right? SIMD registers, if you have such a wide SIMD registers, and if you could go to such a low data, such a narrow data type, then how many operations can you perform in a single instruction? Huge. And that's why it achieves very high throughput. Okay. Now, so vector processor is one where a vector instruction operates on arrays of data. So here, for example, you are operating on an array which has 6 elements. Okay, there are vector instructions to add or multiply 2 arrays of data and produce an array as an output. So a vector instruction can be used to perform all kinds of array matrix and linear algebra operations. These operations form the core of many scientific programs and so on. Okay. So let us see one example. Let us define a vector register, which is 128-bit register. So here, our normal scale register is 32-bit. Okay, but our vector register is 128-bit. So what is the vector length here? Gaurav, what is the vector length here?
4.
4. Yeah, that is the vector length is 4. Okay. Now here, floating point values means 32-bit. So here, our vector length being 4 means it can hold 4 floating point values, or it can hold 8 2-byte integers. 2-byte means only 16-bit. So 16 into 8 is 128. So it can hold 8 2-byte short integers. So this is the most important point. Addition of 2 vector registers is equivalent to pairwise addition of each of the individual elements. This is the whole idea. Although you are, you're issuing an instruction to just add 2 vector registers, but how it is implemented? It is implemented as if you are doing pairwise addition of each individual elements. Okay, and the result is saved in the vector register of the same size. So here is the idea. So here we have, actually we have not discussed what is simple risk, so I will not go into detail. Just I will introduce, I hope till this point it is very clear. Without going into what is simple risk and so on, we suppose have just three vector registers. One is for input, second is for input, third is for output. So we add this and this, store here, add this and this, store here. So now you could define. I will not go into all this. So if there are some vectorization things I have discussed in this presentation, if you have any questions till this point, I will not. Too much of hardware implementation is not required, but just the idea of how a vector instruction, right? A vector instruction. Suppose you have a vector add, how it operates on individual elements. That part should be clear. Is it clear?